Hello and welcome to your second to last unit, probability. Today's just going to be an introduction to probability. A lot of what we talk about today you've probably heard of before. Probability is a little bit different than the other math we've done this year. It doesn't really rely on anything that we've already done before. So some people are really just good at this and they can just see probabilities and they understand it. For other people, it's a little bit of a struggle, but again, it is a different type of math. If you're taking AP statistics next year, these next two units are huge for you because they will show you some of the basics and some of the stuff that you will go over next year too. Okay, so first let's talk just about what is probability. I'm just going to read through this and make some comments. Mathematics of probability begins with the observed fact that some phenomena are random. The relative frequencies of their outcomes seem to settle down to fixed values in the long run. So consider tossing a single coin. It can be heads or tails. The number of heads you get might be is quite erratic in 2, 5, or 10 tosses. But after several thousand tosses, it remains stable, changing very little over further tosses. The relative frequency becomes close to 1/2, and we say the probability of a head on any single toss is 1/2. Okay, so what's that talking about? If you're flipping a coin 2 times, it's very possible that in those 2 times you'll never get tails. So that doesn't mean the probability of getting heads is 100% because you never got tails. Same with 5 times. You could conceivably get 5 heads and no tails. That could happen. It's not super realistic or super likely, but it could happen. If you do 10 tosses, it's even a little less likely. Again, you could get 10 heads. I guess if I gave everyone a coin in my 2 classes and had them flip it 10 times, I might get one person who gets all heads on those 10 tosses, but it'd be kind of rare. But if I asked you to flip a coin 1,000 times, it'd be super rare that you would get all heads. So the more you toss it, it's going to get closer to what's called its theoretical probability of 1/2. Because you know every time you toss a coin, you have a 50-50 shot of getting heads or tails. It says we can never truly observe a probability exactly because you'd always have to continue tossing the coin. It's kind of like talking about what happens as x goes to infinity on a graph. So as the number of coin tosses goes to infinity, the number of heads will come up half the time. And it's like you're getting closer and closer to that limit. In math, we just imagine what happened in an indefinitely long series of trials. That's as x goes to infinity. Some amazing math heroes have tried. While imprisoned by the Germans during World War II, the English mathematician John Carrick tossed a coin 10,000 times. So he kept track of what would happen if he could toss it 10,000 times. He got 5,067 heads, and that out of 10,000 is 0.5067, which is really close to that 1/2. So again, the more you toss it, the closer you're going to get to that theoretical limit of 1/2. All right, so when we talk about probability, we've got some vocab to talk about. An experiment is just a process with well-defined outcomes. So an experiment that we just talked about was flipping a coin 10,000 times. The outcomes could be heads or tails. Outcome is a result of a single trial. So if I do one coin flip, the result of that trial, either heads or tails, would be an outcome. So that's what you want to think of with outcome. Outcome is just a single trial. It's one result. An event is a collection of one or more outcomes. So I want to write an example of an event. It could be tossing tails. That's just one outcome. If I had a coin and a die, it could be tossing heads and rolling a 6. So it's just the event that I'm looking at. Sample space is the collection of all possible outcomes in an experiment. For my coin toss, it's just heads or tails. But if I was tossing a heads and rolling a 6, if I was tossing a coin and rolling a die, my outcome, there'd be more outcomes. It'd be heads in 1, heads in 2, heads in 3, all the way up to heads in 6, or it could be tails in 1, tails in 2, all the way up to tails in 6. Now that we're starting to talk about sample spaces or sets, we can talk about these words: union, intersection, subset, and complement. Union is this little U-like shape, which is nice, U for union. You can kind of think of it as or. All elements of sets A or sets B combined may be in just one of sets or both of them. Kind of the counterpart to that is intersection, and that's the upside down U. That means and. Elements that are in sets A and B combined, what they have in common. When you think of intersection, what do you normally think of? You think of two roads, right? So let's say here's Aralt, and then here's 250. Where's the intersection? Okay, well, again, this road is all Aralt. This road is all 250. But in that, right here, if you were standing right here, you'd be standing in the intersection, which you'd be standing on both roads at the same time. It's what they have in common. That's the intersection. Union would be like if I was standing on Aralt or 250. So the union would be all of this and all of this. So the union is both sets combined, but if they're in both sets, you don't list it twice. Like this part of the road is the same road, whether it's here or here. Subset, all elements in X are also in set Y. We'll talk about that in a second. That's what the symbol looks like. And complement is that little C. So this is set A complement. So it's not in set A. Elements in the sample space that are not in set A. Okay, so let's talk about these real quick. Here's sets A and B, some numbers between 1 and 10, and sets C and D. The sample space S is all integers from 1 to 10. So every number that I could choose is here, and these are all subsets. Determine each of the following: A intersection B. So that's what's in A and B together. Well, they both have a 5, and they both have an 8. So A intersect B would be the set 5, 8, because those are the ones they have in common. B union C. So now I'm looking at this and this. I want to list any number that's in either set, but I'm not going to list it twice. So does either set have a 1? Yup. Does either set have a 2? Yup. There's no 3, there's no 4, but there's a 5. There's no 6. They both have a 7, but again, just list it once. 7 is 7. There's an 8. And they both have a 10, but just list it once. D with a C, that means not in D, D complement. So anything that's in the sample space except 5 and 8. So that you really have to look at the sample space here and list out everything that's not in D. So that's 1, 2, 3, 4, skip 5 because that's in D, 6, 7, skip 8, 9, 10. And when I get a little tricky, like A union B complement, we've got set A. I would list out B complement first. So not in B is 1, there's a 2, so 3, 4, 5, 6, and 9. Now when I want, if it can be in set A, or it can be in this set that I have here, or it can be in both. So there's a 1 in both. There's no 2s, but there's a 3, a 4, there's a 5 in set A, there's a 6 in B complement, there's no 7s, there's 8s and 9s, but no 10s. Okay, and then finally is D, this means is a subset of A. Why or why not? So look at D, 5 and 8. Is everything in D also in A? Yup. So yup. Everything, this is the why or why not part, in set D is also in set A. That's what it means to be a subset. Okay, hopefully that makes sense. There's one on the homework, very similar. Okay, so now let's talk about probability. The probability of an event E occurring is given by the ratio P of E. So this means probability of E is N of E over S of E. N of E is the number of outcomes that fall in event E. N of S is the number of outcomes that fall into sample space S. So if I wanted to say the probability of getting heads, this would be the number of times I got heads over the number of possibilities of me getting heads. So in that prison camp, it was that 5,067 times the number of heads over the number of sample space results, which were the number of times he actually flipped the coin, which was 10,000. Okay, so it's just a fancy way to write what you probably know probability is already. All right, example 1. Experiment is conducted with a spinner, there it is, with 5 equal sectors marked off. What's the experiment? What do you think you'd be doing? The experiment would just be spinning the spinner. It's not writing it very well. Let me try this better. So spinning the spinner. What am I looking for? Yeah, what number it lands on. And noting the number it lands on. Give one outcome. There's lots of options. One outcome would be any individual number. It's just supposed to get used to the vocab. So example, getting a 4. That's an outcome. What's the sample space? Call that S. What are all possible outcomes? 1, 2, 3, 4, or 5. What are the outcomes of the event even? Obviously 2 and 4. What's the probability of spinning an odd number? This could also be written as probability of odd. So it's the number of chances of getting an odd, 1, 3, or 5. So there's 3 options out of the number of possibilities in the sample space, which are 5. So you could write 3/5. You could do what that is as a decimal, and you might know 3/5 is 0.6. So you could say 0.6. Sometimes they list it as a decimal, or sometimes they list it as a percent, 60%. Either of those are fine. What is the event in part E? The event was the specific case I was looking at. So the event was landing on an odd. What outcomes fall into the event in part E? We kind of already talked about that, 1, 3, or 5. What is the complements of evens, or if I said evens with a C? So not evens would be 1, 3, or 5, or odds. So remember, when you see that C, that means not, so not evens. Okay, I think you get that. Based on the basic definition of probability, between what two numbers must all probabilities lie? So what's the probability that it definitely is not going to happen? 0. What's the probability that it definitely will happen? 1. So the answer to this is it's got to be between 0 and 1 inclusive. What's inclusive mean? Just means it can include the endpoints. So 0 is less than or equal to the probability of any event, which is less than or equal to 1. And that's because using the definition of probability, the number of events over the number in the sample space, you could have 0 events in your event. So if you have a 0 probability, it will not happen. For the example, the probability that you get homework after a lesson from me is 0 because you're getting homework. It will not happen. Or you could say the example as the probability of, on that spinner up there, spinning a 7. Well, there were no 7s, so it's 0 out of 5 outcomes, or 0. In contrast, if you have a probability of 1, it will def happen? The probability of me giving you homework at the end of a lesson is 1. It's def going to happen. Or the probability of spinning a 1 through 5, that's def going to happen on that spinner up at the top of the page. So there's 5 possibilities out of 5 outcomes. You have a probability of 1. There you go. Okay. Let's do another example. We've got 2 bags. Set A be a bag with marbles of various colors. The bag consists of 4 blue, 2 red, 2 yellow, and 10 glitter. Set B is a bag with 3 blue and 2 yellows. So if you want a visual, there's my 2 bags. I didn't have a good way to make a glitter marble, so they're green instead. But this is set A, this is set B. What's the sample space of set B? So sample space of set B is all the possible outcomes in set B. So 3 blue, 2 yellow. What's the union of sets A and B? What is A union B? So that would be what would happen if I took my 2 bags of marbles and then just totally dumped them out. So if I dumped them all on the table, I've got, where'd that one go? It's like I've got 2 red, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 green. I should be writing these as I go here. So we've got 2 red, 10 green. I've got 1, 2, 3, 4, 5, 6, 7 blues. And finally, I've got 1, 2, 3, 4 yellows. Okay, so my blues kind of went all over the place. Union is what you get if you just dump everything out. And obviously you could get that without a picture, just by figuring out how many total blues I have, 7, how many total yellows I have, 4, my total reds, total glitters. What's the intersection of A, intersection B? So intersection, again, is what they both have in common. So I could take a blue for a blue for a blue, a blue for a blue. And I could take a yellow for a yellow, and a yellow for a yellow. So they both have 3 blues, they both have 2 yellows. That's intersection. So 3 blue, 2 yellow is equal to A intersection B. But what's 3 blue and 2 yellow also equal to? Just B. Interesting. Which set is a subset of the other? Well, we kind of just saw that. When I did the intersection, everything in B was gone. So that means everything in B was also in A. So B. B is a subset of A. And the reason is because everything in B is also in A. When you have an intersection equal to one of your sets, that means that set was a subset of the other one. So since B was the same as the intersection, B is the subset of A. Write down what a subset of B could be. Okay, well, a subset of B could be anything that contains no more than 3 blue and no more than 2 yellow. So there's lots of answers here. We could do 1 blue and 1 yellow. That'd be a subset. What's another one? Yeah, you could just take your 2 yellows and no blue. You could even do the exact thing that set B is, 3 blue and 2 yellow. That's technically still a subset by the definition. but these are called proper subsets because they're not the entire set. But this is still a subset, even though it's the same, the whole set. Then finally, what's the probability of getting a red marble in set A? So you could write this as probability of red, which would just be the number of red in set A over the total possible values in set A. Okay, so if I reset this one more time, you can see the number of red is 2. 2 out of how many marbles in here? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Looks like 2 out of 18. Which is the same as 1/9. So usually I try to reduce it, but you don't have to always. 1/9 is the same as 0.1 repeat. You can always leave it as a decimal as long as you don't round it. So if I put that repeat part, that's okay. Or you could say it's about equal to 11.1%. Lots of ways to represent a probability. Okay, last two words we need to talk about today are theoretical probability versus empirical probability. Theoretical probability is kind of what we've been doing. The number of outcomes in an event over total number of possible outcomes. What I just did in the last part here was a theoretical probability. We didn't actually pick marbles out of this bag and count. We just thought how many I could get out of how many there were. That's theoretical. So things to remember with theoretical probabilities is you do not need to run the experiment. It's the long run probability in theory. So like when I say the probability of getting tails is 1/2, I didn't actually flip a coin when I said that. I said that if I were to do an infinite number of trials, essentially half of them would be tails. Empirical probability, when you see empirical, that means you're actually doing an experiment. It's the number of, we'll call them successes in the trial over total number of trials. This is when you actually do an experiment. And this is strictly based on observations. It's not theoretically what should happen at all. We would hope that if I do enough trials that it would be close to a theoretical probability. But the example that we did at the beginning of the class that was an empirical probability was probability of getting tails in prison camp. That mathematician that was in prison camp in World War II and got 5,067 out of 10,000. He actually did that. So that was him doing the experiment. It had nothing to do with number of outcomes over total possibility. It came out of number of times he actually got tails, maybe it was heads, I don't remember, over the number of times he did it. Okay, last page. A fair coin is flipped 3 times. The sample space consists of the ordered triples such as heads, heads, tails, HHT, which would represent head on the first toss, tails on the second toss, and a tail on the third toss. Or head on the first, head on the second, tail on the third. Draw a tree diagram to show all the different outcomes. Okay, so you might have heard of tree diagrams back in middle school. First time you flip a coin, it could be heads or tails. If you got heads the first time, you could have gotten heads or tails the second time also. If you got tails this time, you could have gotten heads and tails the second time. So they both branch off like that. If you got both heads the first 2 times, you could still get heads the third, or you could get tails. So basically every column here is another flip of the coin. But since there's different outcomes along the way, it kind of goes and gets larger. It kind of comes out like a tree does. List all the outcomes as ordered triples. How many of them are there? So this is me just following through. Heads, heads, heads is the first one. Heads, heads, tails is the second one. And then I have heads, tails, heads. Heads, tails, tails. Okay, so I've done all the top now. Now I'm going to start down here. Tails, heads, heads. Tails, heads, tails. Tails, tails, heads. Tails, tails, tails. And those are all the possibilities. So that's helpful. That's why tree diagrams are helpful, because you can visualize all the possible ways you could get to your end results. And here and you can figure out how many end results there are. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 outcomes. Find each of the following probabilities based on your answers from A and B. Probability to get all heads. Well, the only outcome that have all heads is heads, 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 obviously. So that's the number of possibilities in the event is 1 out of total number of outcomes, 8. So that's 1/8. How about exactly 2 heads? Well, now there's some more choices. You could get heads, heads, tails. You could get heads, tails, heads. You could get tails, heads, heads. I'm just looking through my list whenever there's exactly 2 H's. So there were 3 outcomes that had those out of the 8. So my probability is 3/8. All heads or all tails? Well, it's obviously heads, heads, heads. Tails, tails, tails. There's 2 out of 8, but that reduces to 1/4. Are your answers in C theoretical probabilities or empirical? Did you actually run the experiment? Did you actually flip a coin 3 times? That'd be empirical. Is this in theory what could happen? Then it's theoretical. And hopefully you can see that it's theoretical, because no one flipped coins in anything we've talked about. So it's theoretical because you didn't actually flip coin 3 times. Okay, last example. A survey was done by a marketing company to determine which of the 3 sodas was preferred by people in a blind taste test. Results are shown below. You kind of do this if you take AP Stats next year. There's a day where you have Pepsi, Coke, and Wegmans Cola, and you see who prefers what. It's kind of interesting. It might not be what you think. Part A, find the empirical probability that a person selected at random from this group would prefer soda B. Express your answer as a fraction and as a decimal accurate to 2 decimal places. Okay, so they call this empirical probability because this is an experiment that was actually run. It's based on observed data. So preferred B, there's 24 people who preferred B out of the total number of people who tried it, which was 53. So that's it expressed as a fraction. And they also want it as a decimal, 2 decimal places. So 24 out of 53 would be 0.45. So sometimes it's easier to have it, or nicer to have it expressed like that, because you can see quicker that that's about half the people, 45%. Find the empirical probability, again, empirical because it's based off of an experiment that was run, that a person selected at random from this group would not prefer soda A. Again, express your answer as a fraction as a decimal accurate to 2 decimal places. Okay, so let's think about what this means. Not preferring A means what? Preferring B or C. So just to get used to notation, I could write this as probability of A complement. That means not A. Or I could write it as the probability that they preferred B or C, kind of like a union. Union means or. Either way, I would add A or B, so the 18 and 24 people out of my total of 53. So that's, oh, sorry. I don't want A or B, I want B or C. So 24 plus 11 out of 53. So it's 35 out of 53. That's it as a fraction. Or as a decimal, 35 out of 53 would be about 0.66. Now, just as one final side note, another way to do not probabilities is to do 1 minus the probability of the opposite thing happening. So remember, the total probability, if they prefer A, B, or C, would have to be 1. You have to prefer one of the three. So take the total possible probability and minus off what you don't want. I didn't want the people that preferred A, so not A. So I could also do this as 1 minus 18 out of 53. This is just 53 out of 53 minus 18, and 53 minus 18 is 35 out of 53, which is what we got to begin with. So just realize that that's also the same as looking at who does like it, 1 minus who doesn't. Okay, give the homework a shot. The thing with probability is every question isn't exactly like what we do in the notes. You should see similar stuff, but just use the notes to the best of your ability. Check your answers and let me know if you got questions. Good luck.